Okay, we're going to talk about power and efficiency now. Now, power in general is just simply the rate of work. So we can think of power then as a force times, instead of a distance, a force times a velocity. And power units are joules per second. So energy per second. So we're looking at kilograms, meters squared per seconds cubed. So it's really getting up there. Energy per second. Instantaneous power is then power equals du dt. We can think of the average power or the slope of the secant line, power curve, or slope of the secant line of the work curve is delta U over a delta T. So with this representation up here, we can think of work as force dot dr, and then we divide that by the scalar dt equals force dot dr dt. So essentially that's force dot velocity. So this was our SI units. In our FPS units, we're talking, there isn't a designation for this. Actually, that's not true. We could have horsepower, and horsepower equals 550 foot-pounds per second. One final term, let's introduce mechanical efficiency. So efficiency equals our power output divided by our power input. Which is the same thing as energy in, so long as the time period that we're looking at is the same, divided by, or the energy out, divided by the energy in. Very weird way to spell the word energy there. Okay, we have a motor pulling on a cable set up in this pulley system that lifts this 75-pound load. So the load will obviously head in this direction. We have a constant acceleration at P developed by the motor of 4 feet per second squared, and if at this point the instantaneous velocity is 2.2 feet per second, what is the power to the motor if our efficiency is 85%? So here we have a situation where we've got two lines leading to AC, so we've got 2AC plus the acceleration of P equals 0. Let's look at free body diagram of C. We're going to end up with 2T pulling on it and a weight, 75 pounds. And this will equal our acceleration of C times the mass. Let's go positive this direction. So our equation of motion then will be 2T minus 75 pounds equals the mass times the acceleration of C, and the acceleration of C is twice the acceleration of P, so we're looking at 4 feet per second. And actually it meant half the acceleration of P based on our relationship. We can then find the tension in the cable of 39.83 pounds. So it's just simply a matter of then figuring out our power. So the power equals our force dot our velocity. And that gives us a 39.83 pounds. Of course, that's this direction. We'll call that just an I. Dot 2 feet per second. Also in an I. And that equals 79.66 foot-pounds per second. So our efficiency for our motor is 85%. So we need 79.66. Our motor then needs to, because of losses, 93.72 foot-pounds per second. And again, this is the amount of power the motor needs to put out because it loses some of this power to different things, vibrations in the cable, friction in the pulleys, friction in the motor itself, heating up in the motor, dissipation of energy, things like that.